on the CMB. And the topic today, since we last time talked about the CMB monopole, meaning the average CMB, today we're going to talk about the fluctuations in the CMB across the sky. And I think this is where it gets really, really interesting, and there's a lot to learn and a super rich phenomenology. So I think this is the lecture that I was really, really excited to prepare. So again, last time we talked about what the CMB is and the average properties. And today we talk about the temperature fluctuations. I also want to say, please keep the questions coming like you did yesterday. I already learned quite a few things actually from a number of the questions. And so I'm excited to hear your questions and to learn from them as well. So yeah, lecture 2, temperature fluctuations in the cosmic microwave background. Oh, I probably need to share them to make them available online. But yeah, I do want to, that's the intention, yeah. Okay, so the things I'm hoping we'll cover today, observed properties of the CMB maps, meaning their fluctuations in temperature, and properties of the CMB temperature power spectrum. Some intuition for Cartesian power spectra, which you've heard about already, and angular power spectra. So hopefully a lot of this you've heard already about from David and others last week. And today we're going to learn how the CMB fluctuations are sourced by inflation or whatever produced the initial conditions, how they are processed by this ionized plasma in the early universe, and what this processing does to the CMB temperature fluctuations, and how they then get projected on the sky for us to see on the sphere. And the goal is that at the very end, once we've understood all this, we can have an intuition for what all the cosmological parameters are doing to the CMB. So this lecture, I think, is a bit of a monster of a lecture. There's a lot in there. And so my goal for today is to go as far as I can today and to finish it tomorrow if needed. So here's a plot that you've probably seen many times. And I don't know if this was your understanding of it. My hope is that by the end, you look at this curve and your understanding will be this. And I'll explain what all of this is throughout the lecture. So, okay, last time we said that the cosmic microwave background was this a near perfect black body that we see in all directions at this temperature of about 3 degrees above absolute zero. We discussed how given the photon to baryon ratio in the universe, we expect that recombination, or when the CMB was emitted, was at a temperature of 3000 Kelvin, and therefore that it occurred at redshift of 1000. We said that this black body spectrum is a sign that the baby universe was in this state of thermal equilibrium, nice and warm. And today what we're going to do is crank up the color resolution or the temperature resolution on this map and look at anisotropies in the cosmic microwave background. So while this color is what the CMB would have looked like if you had been there at redshift of 1000, if you add a few more digits below the decimal points, and if you have a precision of order a few millikelvin instead of Kelvin, this is what the map will look like. And this weird shape here is just the projection, in this projection on the plane, of what a dipole would look like, meaning hotter on one side and cooler on the other side. I should warn you that an unfortunate convention in the color maps of CMB is that typically hot parts of the sky are represented in red and cooler parts of the sky are represented in blue, which is kind of the opposite of what a black body does, but is what your water tap does at home. And so in most CMB temperature map you see, this is the convention. So, okay, the dipole that you see, so the CMB appears hotter in one part of the sky and cooler in the other part of the sky. It's hard to say how much of this is really sort of primordial in what the last scattering surface does, because this is exactly what you would expect from motion. So if you, the observer, happen to be around the Earth, which is zooming around the sun at about 30 kilometers per second, and if the sun is going around the Milky Way at about 200 kilometers per second, and the Milky Way itself is moving with respect to some frame to be defined. All these motions will induce a Doppler shift. And so when you're moving in a certain direction, light from that direction, just the frequency appears higher. So we often call this the velocity dipole in the CMB. And this is not the part that I'll be talking about today. But you can subtract this dipole. It's a near perfect dipole, cosine, so you can subtract it. And then you can keep cranking up the resolution in temperature to look at other features. And this is what a number of experiments have done. The COBE satellites, which first detected the evidence that the CMB was not the same in all directions conclusively. And then more recently, the WMAP and then the Planck satellites have further improved our ability to map the CMB. And when you look at a Planck CMB map, you might see something like this. And sorry if it's hard to read, but here this is plus or minus 100 microkelvin, roughly in the color scale. And with that kind of resolution in temperature, in intensity as a function of patch of the sky, you see all of these red and blue blobs, which are about a degree in size. And hopefully we'll understand soon why it is about that size. And what the color map represents, it's a map of the temperature as a function of position in the sky, meaning what we expect is that everywhere it is a black body spectrum, but one at a slightly different temperature depending on where you look. And the temperature varies by that much. And the thing that's really incredible, I think, is that those patches of the sky that are hotter or colder corresponds to areas in the early universe, in the last scattering surface, that were denser or less dense. And what you're seeing in these patches that are more or less dense are basically sound waves in that primordial soup, sound waves in the plasma of the early universe. And we have a lot of intuition for how sound works. For example, in this room, this sound is slightly different, and we'll talk exactly about how different it is. But what you're seeing here is the surface of last scattering and parts of the early universe that were more or less dense. So it really is a snapshot of the early universe, the baby picture of the universe. Something that's also very interesting from just these numbers, the mean temperature, 3 Kelvin, and the size of the fluctuation, order 100 microkelvin, is that you can quantify, what's the fractional fluctuations in temperature. And so you find 10 to the minus 4, 10 to the minus 5. And in a sense, from this number alone, you can say that dark matter has to exist. And this might actually be one of the strongest evidences for dark matter at all. So let me explain. We see fluctuations in the temperatures across the sky of about 1 part in 10 to the 5 at redshift of 1,000. And we know that today the fluctuations in the matter density field are much larger than this, because what the universe looks like is basically nothing, and then a galaxy, and then nothing, and then a galaxy. So these are very large fluctuations in the matter density field. And you have learned also in the large-scale structure classes that in the matter-dominated era, so for most of the part in the history of the universe, the matter density fluctuations grow as the scale factor. Delta grows as A, and between redshift of 1,000 and redshift 0, you have a factor of 1,000 in expansion. So A has increased by a factor of 1,000, and so if you started with fluctuations in the matter density field of 10 to the minus 5 at that redshift, today they should be 1,000 times larger, and so they should be of order 10 to the minus 2. So what this says is that if the fluctuations in the CMB temperatures that we see, which really kind of are fluctuations in the baryonic matter density, were all there is to it, by now you wouldn't have had enough time, enough expansion to allow those large fluctuations in matter density. So if you start with such small fluctuations and you want to end up with galaxies, you just don't have enough time to do it if you grow as the scale factor. And so what that implies is that while you were seeing those small fluctuations in the CMB, hidden, there had to be something with larger fluctuations in it, and that's the dark matter. And so there's a lot of evidences for dark matter, from rotation curves of stars inside the galaxies, or how fast galaxies are moving within clusters, or strong lensing with the bullet cluster, where you can see that the mass is not where the light is. Those evidences are very kind of easy to understand, but a lot of them are easy to make them go away with modified gravity and things like this. This evidence for dark matter is really hard to go away, because in a sense, if you didn't have dark matter, you wouldn't even have any galaxies at all, of which you could measure the rotation curve or the motion within clusters. So I think this is underrated but extremely strong evidence for dark matter. The fact that there are galaxies at all when you started with such small fluctuations means that there had to be something else back then with larger fluctuations to dark matter. And so this is illustrated in this plot where you see fluctuations in the matter density field for some Fourier mode. And you have different curves there. Black and gray or green here are baryons and photons. And you see those oscillations here, which are the sound waves that we'll talk about. And right, and so you see those fluctuations, and these are the size of the fluctuations you see in the CMB. But while you were looking at the CMB, in the background, the dark matter was actually already collapsing gravitationally. And so when the CMB is emitted, there are actually much larger fluctuations in dark matter that you don't see there. So that's a bit of a parenthesis, but I think it's an important one about how just the mere size of the fluctuations in the CMB is a very, very strong evidence for dark matter. So going back to that map here and trying to understand what it visualizes, I talked about sound waves, and it can be hard to imagine what it means to take a snapshot of a sound wave. And so I was looking on Google, snapshot of a sound wave, and I found this very fun image here taken by Bell Lab scientists. And what they did basically is they had speakers that were generating a standing sound wave in the air. And the way they visualized it is by putting basically a little lamp and a microphone. And the lamp would glow brighter if the sound was large. And they took a long exposure while moving the lamp and the microphone. And so on that exposure, you can see wherever it's bright is where the sound was more important. And that image is kind of what the CMB is. It's the visualization of sound waves in the early universe. And if you think of it this way, as sound, how does one study sound? How can you distinguish, especially when you have sound that seems kind of random? This looks like noise. How do you study the properties of noise? How can your ear distinguish the noise from, a car or the plane or the shower? And the answer is sort of always spectrum. And so when I was young, we had these kind of radios where you had like a built-in spectrum analyzer that would show you how much bass versus how much treble. And so the way you do this is by Fourier transforming the sound, you get the spectrum. And so the CMB is no different. You have this image of what the sound, what this noise looks like, and you can Fourier transform it. So not with respect to time, but with respect to space or angular position. And when you do this curve, this plot, which looks kind of random and basically just like noise, ends up looking like this very simple, smooth curve. And so clearly you're doing something right when you take this map and you Fourier transform it. And why is that? Why is it that the Fourier transform, is the secret key to this message from the early universe? I think we can actually understand this very well. So first of all, our theories do not predict the exact realization of the CMB map. It is noise. We can't really predict that there should be a hot spot here or a cold spot here. But what we can predict are the statistics of this noise. And the Fourier transform is generally a useful mathematical tool whenever you have a system that's translation invariant. So when you have a differential equation where nothing depends explicitly on time, you can Fourier transform it, and you get rid of the derivatives. Now you have an algebraic equation. If you have a system like the universe where you think you should have statistical homogeneity, meaning that on average, no property of the universe should depend on position, and statistical isotropy, nothing should depend on the angle. So you have that translational invariance, and Fourier transform will help. And so I'll say a bit more about this in a moment, but basically, that statistical homogeneity just means that the different Fourier modes are uncorrelated. And so that's a really helpful feature. When you do this Fourier transform and you look at the statistics then of those Fourier modes, which are uncorrelated, you find that they appear extremely close to Gaussian with zero mean. And for Gaussian, you know that the only two pieces of statistical information you need to know the distribution are mean and variance. And in this case, the variance of your Fourier modes is what we'll call the power spectrum. So I know you've heard about this quite a few times already from David and from others last week. And so I'll go through a bit of it again, just because it's very important, but feel free to let me know if that's not useful. Right, because you assume this statistical homogeneity, all the Fourier modes are uncorrelated. Because you find them to be very close to Gaussian, then you know that the only information is in their variance. And so this is why the power spectrum here contains all the information, all the statistical information about this map. For the next couple slides, I'm now just going to go into a bit more detail, starting from power spectra on flat sky or square box, and then generalizing it to curved sky coordinates on the sphere. But let me know if there's already questions before I move on to these two technical slides. Okay, so then I'll tell you more about the power spectrum, and starting from the flat sky. And what I mean by flat sky is if you look at a patch of sky, a few degrees on the side, it might be a good approximation that you don't need to think about the fact that the sphere is curved, and you can just pretend that it's a flat patch of sky. And so when you're on a flat, square 2D box, the way you measure power spectrum, as you've heard, is you basically take your temperature map as a function of position on the sky, and you just Fourier transform. And so here it's a two-dimensional Fourier transform. So you get this T of L vector, where L is a 2D vector, just like you've heard for K in 3D. And so you have this Fourier transform of the map, which if you wanted, you could invert by doing inverse Fourier transform and recover your map. In practice, those Fourier modes are observed to be Gaussian and with zero mean. And when you have a Gaussian variable, again, all the information is in the variance. When you have a Gaussian random field, it's just like a Gaussian vector. All the information is in the covariance. So this correlation function here is just the covariance between temperature here and temperature there. The Fourier transform of this quantity is sort of the covariance between the Fourier modes. So what is the covariance between mode L vector and L prime vector? Now, the CMB appears statistically homogeneous. What we mean by this is that for any amount of translation you could think about, the probability of the shifted field is in all ways similar to the probability of the field. So there's no quantity you could estimate that would be different, so mean, variance, any other higher point function. And you can show that mathematically what this implies is the following. So in real space, it says that the covariance between the temperature here and the temperature there can only be a function of the vector between those 2 points. So the covariance between this point and that point is the same as the covariance between this point and that point. So that's kind of intuitive for translation invariance. And in Fourier space, what it says is that the covariance between two different Fourier modes is 0 unless those two Fourier modes are the same or opposite. And so this is why we say statistical homogeneity implies that the different Fourier modes are uncorrelated. So this is uncorrelated, but if you're uncorrelated and Gaussian, then you are independent. And so each Fourier mode you measure is just completely independent. Now, another property is statistical isotropy, meaning you're not just invariant under shifts, but you're invariant under any possible rotations. And if that's the case, then the correlation function between 2 points doesn't just depend on the velocity vector between these 2 points, it depends only on the distance between these 2 points. So again, I think that's quite intuitive. And in Fourier space, what it implies is that not only your Fourier modes are uncorrelated, but the power spectrum here is not a function of the L vector, just the modulus of the L vector. And so with all this, what it means is you start from a map of the CMB. In practice, that map might have something like a million pixels or a million Fourier modes. And you have compressed it to a function of just one scalar quantity, the L modulus. And you can get away with, say, 1,000 of such modes. And so you have not lost any statistical information, but you have compressed your data from a million Fourier modes to just about 1,000 power spectrum values. So you've reduced the size of your data by a factor of 1,000, which is always helpful for data analysis at no cost in statistical information. So this slide is all I was going to say about power spectrum in flat space, and I'm then going to move on to curved sky. But yeah, if there's questions, please interrupt. Mm-hmm. Right. Thanks for the question. So I think the question is, how large can I make my patch before I have to worry about curved sky effects? And I think that's a really good question. And of course, that's always something you can test for. You know, if you're extracting a patch of your sky, you can both compare your results with the analysis of the actual curved sky and see what matters. The answer will depend on the scales you care about. If your analysis is in Fourier space, and you care about very small scale modes, you can often get away with flat sky approximation. And if you care about large scale modes, you know, the kind of modes that might vary just only once or twice when you go around the full circle, there the flat sky will be a very bad approximation. Yeah, it's kind of low L versus high L. And quantitatively, where exactly is the cut will depend on the kind of precision you want on your observable and its power spectrum. Right. So working in the flat sky is an approximation. So if you can get away without it, then if you do it on the curved sky, you'll have the right answer for sure. The only trade-off is that computationally, it can be harder to do spherical harmonic transforms, which I'll describe, rather than Fourier transform. So both in terms of data analysis and in terms of analytical predictions, if you can get away with flat sky, go for it. And if you don't need to, then no need. Yeah. Thanks. And I think there was another question, maybe. Oh, yeah. Right up. The statistical isotropy, for example. Yeah, actually, there's various ways we test this assumption. And one way is to, you can think of taking a small patch of sky and measuring the small scale fluctuations, and then looking at a different patch of sky and measuring the same small scale fluctuations, and asking, do they have indeed the same power spectrum? And in fact, we implicitly test this when we do things like CMB lensing measurements. In a way, that's kind of what CMB lensing estimators are. They look at variations in the local variance of small scale modes. They ask, how does the variance in the small scale modes vary on large scales? In fact, we do see such variations, but they're understood as being produced by lensing and very consistent with being from lensing. So yeah, we do test this assumption, and that'll be the topic of lecture 4, hopefully. But yeah, thanks a lot. Any other question on this? Okay, so then let's move on to curved sky. And I should admit that as a cosmologist, I have still lived most of my life on the flat sky, and so there's still a lot you can do with simple Fourier transforms. So moving on to curved skies, so if you're looking at variations on large angular scales, you can no longer neglect the curvature of the sky. And so how do you generalize this Fourier transform to the case of curved sky or on the sphere? So the idea here is the reason Fourier modes were so useful is because they were eigenvectors of the Laplacian in flat space. And so you can ask correspondingly, what are the eigenvectors, the eigenfunctions of the Laplacian on the sphere? And the answer is these are the spherical harmonics. So I won't give you more about the definition, mathematical definitions of the spherical harmonics, but I'll just show you what a few of them look like. They're determined by two numbers, which actually as cosmologists we call L and M, as opposed to N and M. And basically the first number, this L here, tells you roughly how many times, how many bumps, and troughs you see when you go around the full circle. So L equals 0, you see none, the field is constant, so that's what we call the monopole. L equal 1 is the dipole, meaning a peak on one side and a trough on the other side. L equals 2 is a quadrupole, so when you go around the circle, you see peak, trough, before you come back, and so on. L equals 3, you'll see 3 oscillations, and so on. And for each of these L values, you have a number of M values, which basically just tell you how the spherical harmonic is oriented on the sky. These spherical harmonic functions are an orthonormal basis, which means if you take this scalar product between two spherical harmonics with different L's and M's, you find 0. And if the L's are equal and the M's are equal, then you find 1. And any function on the sphere, so for example, this function f would represent the temperature of the CMB. Any function on the sphere can be decomposed as a sum of spherical harmonics times some coefficients, Lm, FLm, which are the decomposition of your function in spherical harmonics. So this is very similar to the Fourier transform, except the basis now, instead of being plane waves, is those spherical harmonics. Equivalently, the same as you have, inverse Fourier transform and Fourier transform, you can get the map from its spherical harmonics coefficients, or you can get the spherical harmonics coefficients from the map by integrating it with respect to the complex conjugate of the spherical harmonic function. Again, once on the sky, you no longer have this on the sphere. You no longer have this notion of statistical homogeneity because there's no more shifts. Everything is a rotation, and so you talk about statistical isotropy, that the properties of your maps don't change if you rotate it by any amount. And this implies a very similar thing to the case of Fourier transform, which is before we had that the different Fourier modes were uncorrelated. Their covariance was 0 unless they were the same Fourier modes. And so the same is true for spherical harmonics due to the statistical isotropy. And just like before, where the correlation function and the power spectrum were Fourier transform of each other, you have this relationship between the correlation function, the covariance between temperature here and temperature there, relating it to this CL, this power spectrum, where PL is a Legendre polynomial, depending on the distance between those 2 points. So this defines the spherical harmonics, decomposition, and the power spectrum. Another way to think of the power spectrum is that it is, like before, the expectation value of the mean modulus, of the modulus squared of your ALMs. So again, just like before, you had Fourier transformed your map, and you ask what is the variance in that Fourier mode. Here you have done a spherical harmonics transformation of your map, and you ask what is the variance in the spherical harmonics coefficient. So the power spectrum is an expectation value. So the idea of those brackets, this expectation value, is if you could have many different realizations of the CMB, in each of these maps you could measure that ALM value, and across all those maps you could ask, what's the variance in those ALMs. But in practice, of course, we only have one CMB sky, so we cannot estimate this expectation value. But something that helps us, again, is that just like before, where the power spectrum depended only on the modulus of the L vector in flat sky, now the power spectrum depends only on the L value, not the M. And so you have only one sky, but for each L value, you have a number of M values. You have exactly 2L plus 1 of them. And so what you can do is you can measure the different ALMs with the same L, and you can estimate the variance this way. So I think this is similar to the discussion of ergodicity you had yesterday. but you only have one CMB sky, but the CMB sky has many, many Fourier modes or many spherical harmonics, and a lot of them share the same power spectrum. So all the ALMs with the same L share the same CL, and because you have a number of them, now you can estimate this variance from all these Fourier modes. Something that you've probably heard about as well is that, again, because you're averaging a finite number of Fourier modes to estimate this power spectrum, this estimator, this estimated power spectrum, has an irreducible variance, which we call cosmic variance. And the way to think of this is you have only one CMB sky, or maybe another way to think of this is the power spectrum is the variance of the field, and you have only some samples of some realizations. So if you think of throwing a dice and asking what is the variance of that dice, so I throw my dice, I get a number between 1 and 6. I could do it many times, and I could try to estimate the variance of my dice. A confusion that you often hear is, oh, I have only one sky that I get to observe, so I have only one throw of the dice. So how am I going to do? And the answer is, well, you have only one realization of the sky. You don't have just one throw of the dice, because you have many, many, many Fourier modes. And so you have as many throws of the dice as you have Fourier modes. And that's why you can actually measure or estimate these statistical averages. Any questions about this part? Okay. So moving on to what the power spectrum looks like in practice. So CL is the power spectrum. Oh, there was a question? Yeah, I'm sorry. Right. Yes, that's a really good question, because I think that's a very important point. You indeed have only one realization of the sky, but as we've discussed, because of statistical homogeneity and isotropy, all the different Fourier modes are statistically independent, or all the spherical harmonics are statistically independent. And so what it means is that every spherical harmonic coefficient you have is a different realization of a random variable. And if you take all the ALMs with the same L, they are all independent draws from the same power spectrum, the same CL. And so how many throws of the dice do I get to measure CL? I actually get 2L plus 1 of them. And this also explains why, when you're on small scales, high L, the uncertainty goes down because you have many throws of the dice. And when you're on large scales or low L, this 2L plus 1 becomes a small number. You have few throws of the dice, and therefore the cosmic variance is larger. And this is what you can see in typical plots of the power spectrum is at low L or large scales, you have this large uncertainty from cosmic variance, which disappears on small scales. You'll often hear about or see about the power spectrum CL. You'll often also see this DL, which is basically L squared CL at high L. And this is a form of power spectrum that's dimensionless, contrary to CL. It is dimensionless, and it tells you how much variance you have per logarithmic band in L. So this is a quantity that people like to plot. It's also a useful one because in these units, a scale invariant power spectrum would be a flat curve. So L squared CL or K cubed P of K in 3D are the reasonable dimensionless power spectra. So just to give you an intuition, how do L values map to angular sizes? The rule of thumb is just like in a Fourier transform, L equals 2 pi over theta. So maybe I'll just write this so we don't forget. L equals 2 pi over theta. So where theta is the angular wavelength of your mode, the corresponding L is as follows. And so when you have large thetas, this is small l's, and vice versa. And so what the little colorful maps are trying to show you is what a map would look like that would have either this power spectrum or that power spectrum on the corresponding scales. So high L's describe very small scale fluctuations, and low L's describe a large-scale fluctuation. Okay, so this is what a power spectrum is and what this DL is that's very often showed in CMB. Yes?
Does cosmic variance also limit the accuracy with which we measure the monopole or the dipole, or do you think it can get measured by the average?
That's a really good point. So when you're measuring the monopole, there you really just get one throw of the dice. And this is not stuff that I think about very often, so I may say something silly, and please anyone correct me. But you could imagine, on the size of the observable universe, you could imagine fluctuations that are much larger. And so we might happen to live in an overdense or underdense region of the universe, which would change our monopole. So I think that's correct. I suspect from inflation, if you assume an almost scale invariant power spectrum, you can actually quantify what's the typical variance in the monopole, for example. But yeah, I think that's a good point. Cool. So this is the power spectrum, and in practice, if you please, we'll look only at this top curve for today. We'll talk about the other ones tomorrow and maybe the day after. So again, this is this DL, this dimensionless power spectrum, and this curve is for temperature as a function of multipole. And what you can see is many experiments have put data points on this curve, and you can barely see the error bars on these measurements. And so this CMB power spectrum has been measured extremely well. And what you can see is that not only it has been measured incredibly well, but the data points seem to fit very well this dashed line, which is actually a theoretical prediction. And this theoretical prediction is based only on a handful of parameters. And so with only of order 6 or 7 parameters, you can actually, and very simple physics, you can predict this curve. And this curve happens to describe extremely well the statistics of the millions of pixels you can see in CMB maps. So the goal for today will be basically to understand where this theoretical curve comes from and what's the physics inside of it. Any other questions for now? Yes? Oh, right. So yes, so this curve shows a number of auto and cross spectra. And so it's called DLXX, where X can be anything. If the X here is temperature, you get DLTT, meaning the auto spectrum of temperature. We'll hear hopefully tomorrow, if I make enough progress today, about those E and B modes of the temperature. And you may have heard about them already in Lensing or other things. Okay. Yeah. Cool. Okay, so how do we understand the CMB temperature power spectrum? There's really a few steps. The first one is the initial conditions from inflation. So the kind of universe that inflation left us with, what were the fluctuations in there. And you've learned last week about the fluctuations in this comoving curvature parameter that you can think about like a gravitational potential, and whose power spectrum is almost scale invariant. And so in those units of delta squared or D, which is the same thing, a flat curve with a very slight red tilt. So these are the true sort of initial conditions after inflation for the rest of the universe. Fluctuations on all scales, almost scale invariant. And then these fluctuations get processed by the plasma. And what I mean by this is that you have a medium, whether it's the surface of a pond or the air in this room. If I put some initial conditions in there, if I take this room and I compress half of the room and expand the other half, once I let it go, it's not going to stay like this. The thing is going to evolve. Waves are going to propagate. And so this is what I mean by processing of the initial conditions by the plasma. And so this is going to happen until the time the CMB is emitted. So these initial conditions from inflation are then going to evolve in time. Those sound waves are going to propagate until the CMB is emitted, at which point things change, no more waves. The photons just propagate all the way from the last scattering to today, and eventually get projected on the sphere when we look at them on the sky. And so if we put together the initial conditions from inflation, the processing by the plasma, the propagation between last scattering to today, and the projection on the sky, you can actually you can see how this flat spectrum would turn into these bumpy, wiggly spectrum that we see in the CMB. And so the goal for today and part of tomorrow will be to understand each of these steps to see how this curve comes about. And this equation is a good summary for how this works. So the power spectrum you see today at a certain L is the result of the initial power spectrum in this co-moving curvature perturbations. These initial fluctuations are processed by the plasma, and this is a linear transfer function that tells you how given Fourier modes evolve all the way until the time of last scattering. And then finally, those modes get, they free stream towards us, and they get projected on the sphere of the sky, and this is what those spherical Bessel functions do. So I'll talk about each of these in turn. I'll do them in a slightly different order. I'll start with the summary of the initial conditions from inflation. And so if I say anything silly about this, or if you have any questions, thankfully we have Gonzalo in the room. And then I'll talk about the propagation from last scattering to today and how it projects on the sphere. And then finally, the bulk of it will be the physics of this transfer function, how fluctuations propagate in the early universe's plasma. Yes? A good question. I think it's pretty close to exact within linear theory. Meaning to describe the evolution of a Fourier mode K as just multiplication by a transfer function, that is linear theory, where you just have a K-dependent growth. Yes, so the Boltzmann hierarchy in usual calculations is linearized. So the Boltzmann hierarchy, to start with, is a nonlinear hierarchy, but you can linearize it. And when you solve this linearized Boltzmann hierarchy, you end up with this transfer function that you can then use. Yeah, thanks. Okay, so let's start with the initial conditions from inflation. And I will start with just sort of my one slide summary of my understanding of it and the key qualitative features that I take away. And so inflation is the hypothesized phase in the very, very early universe, in the first few fractions of a second that produced the initial conditions today. Inflation was originally motivated to solve background considerations in the universe. So I'm sure you've heard about the horizon problem, curvature problem, or the absence of magnetic monopoles last week. And so these are interesting problems in the universe on large scales. They have to do with the background universe. And so inflation was a phase of accelerated expansion that allows to solve these problems and make them go away. But when you take inflation seriously, if you've introduced this scalar field, the inflaton, and you think it truly is a force of nature, it truly is a quantum field, then you will generically find that this quantum field will have quantum fluctuations. And so I think one thing that made the whole inflation paradigm very compelling is that while it was introduced only to solve those background problems, it for free predicted many properties of the fluctuations. And a lot of these properties are actually what we see in the CMB. So, okay, the picture is those quantum fluctuations in the inflaton, for example, get stretched to very large scales. And once they're stretched beyond the Hubble scale, two things happen. Once these quantum fluctuations become effectively classical, and two, they become frozen, meaning they no longer evolve in time. Those fluctuations, if they're the fluctuations in a free field in its vacuum, should be Gaussian. And indeed, this is very much what we see with the CMB temperature fluctuations. If you're in that phase of accelerated expansion, the power spectrum is basically scale invariant. But because inflation has to end, you know that you should have a slight red tilt in the primordial power spectrum. And indeed, this is very consistent with what we see, an almost scale invariant power spectrum with a slight red tilt. In the case of single field inflation, inflation is basically a single clock inflation where inflation just ends at a slightly different time at different positions in space. And this produces a very specific type of initial conditions that we call adiabatic. Basically, The reason there are fluctuations, this part of the sky is a bit overdense versus that one, is just because one of them is a bit late compared to the other. They're the same, but just slightly shifted in time. And if you take a universe and you just shift it a bit in time, what happens, since you know how matter and radiation redshift differently, you expect a certain ratio between their fluctuations. And these adiabatic initial conditions is what we seem to see in practice. It also predicts perturbations that you might call acausal, and maybe I'll explain more what that means when we talk about polarization. And very, very crucially, it predicts a phase coherence between the different Fourier modes. And what I mean by that is if you take all the Fourier modes with a same modulus, they all start to oscillate at the same time, not at random time. They're all in phase together. And I think this is a crucial bit. And if you didn't have this, you wouldn't actually see all the BAO bumps in the power spectrum. And I'll explain why that is in a moment. You may have heard concerns about this whole paradigm of inflation. And there are arguments that inflation was set up to solve problems, the fact that some parameters appeared fine-tuned. There may be senses in which the initial conditions for inflaton and inflation are perhaps more fine-tuned than the problem it tries to solve. There may be concerns that because you have so much freedom in what you assume for this inflaton or other fields, it may be hard to falsify inflation scenarios. But I think it remains a very good way to think about the initial conditions for the universe. And so for now, I'll assume that this is what happened. Question? That's a good question. I think a lot of these problems are kind of the same problem about basically the size of the causal horizon as a function of time. I probably can't derive it here, but I think you can sort of express all these problems as the same thing, like the size of the causal horizon versus the size of the universe. Maybe, I don't know if you have more to say on this, Gonzalo?
It's my fault because I never mentioned the bubble problem.
Oh, no worries.
You mentioned the horizon and the truthful problem. Perhaps we can talk about it later in the Q&A.
Sounds good, yeah. So please keep your question and we'll cover it. Okay, so we have all of these really non-obvious properties for the initial conditions that we seem to see in the CMB and that are sort of natural consequences of inflation. Yes? Yes, I'll say a lot more about this in a moment. So, if you're not satisfied, please ask again at that point. Thanks. Okay, and so from our perspective, these will be the starting point. So again, that dimensionless power spectrum, we saw that in 2D was L squared CL, in 3D it's K cubed P of K. And for the scalar perturbations, the perturbations in sort of density field, the relevant power spectrum is that of this comoving curvature perturbation, which in my head I sort of just think as a gravitational potential. And this power spectrum is almost flat with a certain amplitude AS. If NS, which is how we define this scalar tilt, was exactly 1, you would have a flat power spectrum. NS is slightly less than 1, and so you have this slightly red, almost scale invariant power spectrum. You can relate the amplitude of the power spectrum and the slope to quantities like the Hubble scale during inflation and the slow roll parameters. And so I think you've learned about this. And for tensor perturbations, so not fluctuations in sort of density or the potential, but fluctuations in gravitational waves, you have a similar power spectrum with an amplitude and a slope. And again, in slow roll single field inflations, you can relate the amplitude and the slope to Hubble and the slow roll parameters. And in this simple model, you can even predict the relationship between the amplitude of the tensor and scalar perturbation. So I'm sure, I think this was covered last week way better than I'm doing it today. So this is just a reminder because it will be our starting point for the CMB. So again, going from initial conditions to the CMB, here is the power spectrum of the gravitational potential or the comoving curvature perturbation, an almost scale invariant power spectrum with a slight red tilt. I'm now going to move on to the propagation of the photons from the CMB, from the last scattering surface to today, unless there's any other question on the first part. Mm-hmm. Oh, yes, so I think that was the question that was asked. I will answer this question in number 3 when I talk about processing by the plasma. And I'll try to make that relation really clear because it's a really important point. Cool. Okay, so number 2, propagation of the photons from last scattering to today and how they project onto the sky. First, I wanted to start with this equation, which is a really important one, and it relates the fluctuations of temperature that we see today to the fluctuations of temperature at last scattering and other properties at last scattering and between last scattering and us. So hopefully this is readable. The CMB temperature that we see today is related to the CMB temperature that was out there at last scattering. So that part would seem like the equation perhaps you would have written. But there's other terms. One is the gravitational potential of that position at the last scattering surface. And really, I should write the difference between the gravitational potential here and the gravitational potential at our location. And this term is a gravitational redshift effect. So it just says, okay, that patch of sky perhaps was overdense and hotter. And so the photons there had more energy. But for them to reach me, they have to escape that patch. And so if that patch of sky was overdense, it probably also was a gravitational potential well. And so the CMB photon, to escape that potential well, had to lose some energy. So there's this gravitational redshift effect. Another effect is Doppler, and it depends on the velocity of the plasma at that location. And this is just saying, you know, that patch of sky is a plasma at a certain temperature, but if it was moving towards us, due to the Doppler effect, the photons get a boost in energy. And so we should see a higher temperature. And conversely, if they're moving away from us, they should lose energy from this Doppler effect. So here what matters is the velocity projected along the line of sight. So the velocity towards or away from us. Okay, and so all these quantities are properties at the last scattering surface. So how hot was it? Was it in a potential well? How fast was it moving? So all of these are features of the last scattering surface. And finally, there is this last term here called the integrated Sachs-Wolf, which actually is an integral between the last scattering surface and today. It's an integral of how much the potentials have changed with time. And we'll talk more about this, but the idea here is that if there's a potential well between the CMB and me, photons will go down the potential well, gain energy, and then they will leave the potential well, lose that energy, so no net change. But if the potential well is changing in time while the photon is going through it, you can get a net change in energy. We'll talk about this. And so I will focus a lot of this talk on these two terms, which together we call the Sachs-Wolf term. So the sum of how hot it was and how deep the potential well was there. And some really interesting thing is that when you have a plasma and you compress it, how much hotter it gets and how deep the potential well gets are related. And so those two quantities are actually connected. And you can see how they are connected. So the change in the temperature is related to the change in the photon energy density. This 1/4 here just says that the energy density goes as temperature to the 4th. And so fluctuations in the energy density are 4 times the fractional fluctuations in temperature, hence this factor of 1 to the 4th. But you can also relate the fractional changes in the photon density to the potential. And you can actually show, I'm not going to do it here, but you can show that the sum of these two terms, the Sachs-Wolf term, is actually equal to the potential divided by 3. And so if you think only about this term in your CMB temperature map, which is a very important term, the temperature fluctuations you see in the CMB are actually fluctuations in the gravitational potential. So I said that the CMB was the baby picture of the universe, was the initial conditions of the universe. It is really the initial conditions in gravitational potential. So that map of the CMB is a map of the gravitational potential of the universe. And something very interesting is that if you are in a patch of the sky that's hotter, if that blob was hotter at the last scattering surface, it was denser, its potential was negative. And so if the CMB there was hotter, the CMB you actually see has the sign of phi, it will be negative. So overdense regions at the surface of last scattering appear less hot to us. So hot spots are cold spots, and vice versa. And the reason for this is, that part was hotter, it was denser, but the energy it took to escape the potential well was more than the extra energy it had from just being hotter. So on large scales where this Sachs-Wolf term dominates, hot spots are cold spots, and vice versa. I'll say a lot more about the physics of this, but really I just wanted to make the connection between what happens here when we look at the CMB versus what happened there and what happened in between. And now I'm going to talk about projection from 3D to 2D, but if there's any question, yeah. Shallower. Right, so you can compute how density contrast and potentials evolve as a function of the expansion. There's some gauge dependence on large scales, but yes, so things will change, the fluctuations will change. But here we're really just looking at phi at that time, phi there. Projections from 3D to 2D. Oh, sorry, question.
For the Sachs-Wolf component,
Mm-hmm.
which of the two components connects to the curve of the first equation? Or the connection to the primordial initial condition is to phi instead?
Yeah, so I think the answer is they all connect to phi. So basically in these adiabatic initial conditions, you only need to know one scalar number, and that can be r or phi. And everything else can be derived from phi, so delta, gamma, etc.
Right, but delta t over t and psi are different things, right? One of the quantum only and the other is potential.
Right.
So I understand that both of them connected, but they evolve differently.
Oh yes, they will evolve in time slightly differently, but they are related like this. I don't know if that makes sense. Yeah, maybe we can talk more about this. Yeah. Okay, so projection from 3D to 2D. So I apologize for the very busy slide. The only thing I would like you to talk about, to look at right now, is in this diagram on the left, you see a plane wave in faded gray and blue. Blue and red. So you have a plane wave that propagates in this direction. And so maybe you have under density, over density, under density, over density. And the only thing I want you to look at is how this plane wave propagates, converts if you project it onto a sphere. And so here you have a sphere that you can think of as the last scattering surface that we see. And so you can see how this plane wave gets imprinted into density fluctuations on this last scattering surface. And what you can see is that a plane wave has a fixed wavelength in the linear direction. When you imprint it onto the sphere, you can see that the wavelength in angular direction is no longer constant. So here, for example, things vary fast, and here you can see that things vary slow. And so what that tells you is that when you convert the Fourier modes k into the spherical harmonics L, the relationship is not quite one-to-one. So you can ask, for example, if I look at a fixed k mode, like a fixed plane wave, if I give myself a fixed L mode on the sphere, which are the k modes that are going to contribute to it the most? And you can see that depending on the L mode you look at, the answer is a curve, and that curve is the spherical Bessel function. And because that curve is a curve and not just a delta Dirac, there isn't a one-to-one mapping between K and L. But this Bessel function tells you exactly how each of the Fourier modes, whose evolution you can predict, will propagate to each of the L's. So I have a couple busy plots here, which translate from L to K, depending how you slice this Bessel function. But yeah, basically the answer is JL, the spherical Bessel function for mode L, evaluated at the product of Fourier modes times the radius of the last scattering surface. So that's kind of all I wanted to say. The mapping between L and K is not one-to-one, but in all these cases, it peaks at L equals K times Chi star. So to 0th order, you can think that the L modes, a given L mode tells you about a given K mode with this translation, but you should know that it's a bit broader than this. It's not just a one-to-one mapping. Okay, and so at this point, we have this mapping between K and L. This tells you that if I were to change the distance between the CMB and us, if I change this co-moving distance chi, and if I change nothing about the physics, so nothing about the K, I'm really just rescaling the power spectrum in L. And so this is already enough information to understand one of the parameter dependencies of the CMB power spectrum. So even without understanding anything about what this curve is here for the CMB power spectrum, you can see that cosmological parameters that change the distance to the CMB will basically just shift this power spectrum curve left and right. And because of that, there's a degeneracy between cosmological parameters in the CMB that we call the geometric degeneracy. And this degeneracy just says that if you change cosmological parameters in a way that does not change the distance to the CMB, you might have a degeneracy between these parameters. And so here, for example, you see constraints from CMB experiments, and this broad band here is from CMB, temperature polarization. And you can see that it's a very narrow band, which is what a degeneracy, an almost perfect degeneracy looks like. And so when you change this parameter, omega matter, curvature, and the Hubble parameter today, when you change them by staying on this line, you do not change the distance to the CMB. And so the CMB cannot really tell them apart. You can break this degeneracy if you include observables at later times, which can help. And so these can be gravitational lensing of galaxies or of the CMB, or baryonic acoustic oscillations. Okay, so this is all I wanted to say now about this propagation from last scattering to today and the projection onto the sphere. I will now move to the physics of those oscillations inside the plasma, unless there's a question. Okay, so processing of the initial conditions by the plasma. How does that work? So again, the idea is that inflation imprinted those fluctuations in density or in the potential in the primordial plasma. And a key feature of inflation, again, is that those fluctuations were frozen. Once they're stretched beyond the Hubble scale, they do not evolve in time, they're frozen, and they remain frozen until their wavelength crosses the Hubble scale again. And when that happens, so once the wavelength is now within the Hubble scale, these fluctuations will start evolving. And it's really just like sound waves in this room. If you started with a pattern of overdense and underdense region and you let them evolve, they will oscillate, the waves will propagate. So these are self-gravitating sound waves, so it's a little bit different from the sound waves in this room. It's different in several ways. So one, the restoring force here is actually radiation pressure, as opposed to the thermodynamic pressure of the baryons. So you have to imagine that when you compress the air in this room, you have pressure, and that's the restoring force. Here in the CMB, the restoring force was actually the radiation pressure from the photon. But these are also self-gravitating, which means that when you compress the air in this room, things get denser, and so yes, the gravitational potential has deepened, but in this room, that's not an effect that's really important. For those oscillations in the primordial plasma, this effect is important. So when you compress the gas, the potential gets deeper, and that's a force that sort of goes against the radiation pressure. And finally, to have oscillation, you need a spring, you need a restoring force, but you also need some inertia. Inertia is the thing that makes you bounce back too far and therefore keep oscillating. And here the inertia, sort of the mass in this fluid, comes from the energy and pressure densities of the photons and baryons. And so when you're deep in the radiation era, the energy density in baryons is negligible, and so all the inertia is from photons. And when you're deep in the matter era, which you really aren't for the CMB, then most of the energy density is in the baryons. And so I was trying to come with an intuitive picture for what this means, but the closest I could come up with is imagine the surface of a lake with ripples, and imagine that somehow the lake was frozen with those ripples imprinted on it. And then at a certain time, which for us is this Hubble reentry, at a certain time you allow the ripples to start evolving, and they will start wiggling. And then at a certain later time, you just take a photo of the lake, and that photo is your CMB. So this is really the picture. You have the initial conditions from inflation, they're frozen, all of a sudden they start evolving, and at a fixed time later, you take a photo. Okay, and so now is the part where I would like to explain to you why it's so crucial that things are frozen in, and that you have this phase coherence, and that everyone starts oscillating at the same time. And so I'll explain a bit of this, and then I'll try to make a cryptic drawing on the board, which hopefully will help. So, okay, you have this tightly coupled photon-baryon plasma. And so the protons, the electrons are tightly coupled to photons via Thomson scattering. So this is what we talked about last time. And all of a sudden, at some redshift of about 1,000, because you have recombination, all of a sudden this stops. The photons are no longer tied to the baryons, and this is when the snapshot is taken. So again, the picture is you have a start for the oscillation, which is the Hubble reentry for your Fourier mode, and you have a stop, which is recombination, and we get that snapshot. And so the idea here is that you start with a certain power spectrum of fluctuations. And so, thank you. You have the power spectrum of oscillation that's almost flat, so I'll just draw it as flat. And none of these fluctuations are evolving at first. Everything is frozen. And as time goes on, first the small scale fluctuation and then the larger and larger scales will start evolving in time. So this is my initial power spectrum before anyone has re-entered the horizon and started oscillating. And those modes will start first, and then these ones, and then these ones. But an important factor as well is that they oscillate at different frequencies. So when you have a sound wave, you have a dispersion relation. So frequency is related to the wave vector or the wavelength via the speed of sound. And what that means is that if I consider a standing wave in the pressure, that wave will oscillate at a different frequencies depending on its wavelength. And a low frequency wave will just oscillate very slowly. And a very large wavelength wave will oscillate slowly. And a very small wavelength wave will oscillate very fast. And so when I allow these different Fourier modes to oscillate, this plot I think of as a plot of the amplitude of each Fourier modes. These modes will start oscillating up and down, and they will oscillate very fast. These modes here will oscillate very slowly. And so if I take a photo of this power spectrum at a slightly later instant, all of the modes want to oscillate up and down, but the large-scale modes haven't started oscillating, and the small-scale modes have started. If I take the photo a bit later in time, I'll see something like this. And if I continue allowing the system to evolve, I'll see something like this. And so at a certain time, if I were to take a photo then, I would see 0 power spectrum in these Fourier modes. But if I keep going, the modes oscillate. They start bouncing up and down as time goes by. And eventually, you might see something like this, where certain modes have had the time to do multiple oscillations, and some modes are only at their first 0 crossing. So if this is the picture, if I take a photo at this moment, I will see a power spectrum with bumps and wiggles, very much like the CMB bumps and wiggles. even though I started from this flat power spectrum, just because the small scale mode oscillate faster than the large scale modes. Question? Mhm. Yes. So in a sense, you can think of the power spectrum here at any given time as being the convolution of the initial power, sorry, the product of the initial power spectrum and that transfer function squared. And so what you can see here is, in this curve, there are modes where the power spectrum is exactly equal to the original power spectrum. And these are the large-scale modes that haven't had the time to evolve at all between the end of inflation and the CMB. And so when you look at these scales in the CMB, what you see is really the initial conditions from inflation. And then once you see the bumps and wiggles, you're no longer seeing just the initial conditions. You see the initial conditions having oscillated a certain number of times. And so hopefully this intuitive picture helps you understand why you see those bumps and wiggles. What it doesn't explain yet is why some bumps are higher than the other. But the low L's here basically map to these low K. And so here you're roughly seeing for the Sachs-Wolf term the initial conditions. And here you're seeing a different number of compressions. So the first, these modes oscillated only sort of not even once, they just compressed once. These are the modes that just happened to go through 0 when the photo was taken. And these are the modes that went through 1 compression and then 1 rarefaction, and so on. Okay, so this explains the bumps and wiggles. And this hopefully explains why why the coherence is so important for seeing these bumps and wiggles. Because the idea here is that for a given K modulus here, I have many different Fourier modes K. And the point is they all start oscillating at the same time. And so they're all in the same exact phase of the oscillations. So they're all, for example, at their first compression, or they're all at their 0 state. And this is not what happens, for example, if you take a photo of the surface of the sea or a pond, because the different Fourier modes of the same wavelength are just all in their own phases. And so some of them might be at 0, but some of them might be at the maximum of their oscillation, and you won't see those bumps and wiggles. So for you to see, for example, 0 power spectrum means that all the modes with that same wavelength are going through their 0 moment of their oscillation. I hope that answers the questions about why the phase coherence is so important. Otherwise, please feel free to ask. Mm-hmm. That's right. And sorry, yes. I think that's. Mm-hmm. Mm-hmm. Right. So I think this is yet a stronger statement than the statistical homogeneity. For example, if I pretend that the sea is infinite, and I look at the power spectrum of the waves at one spot or at another, it'll be the same. So I have this statistical homogeneity. But I don't have this feature that no matter the direction, all the waves have the same exact phase. So yeah, having the same phase as a function of direction is like an isotropy statement, but it's a stronger isotropy statement than the statistical isotropy. Yeah, thanks. Okay, and so by looking at the spacing of these bumps and wiggles, what you learn about basically is this dispersion relation. And so you learn about the speed of sound, and you learn about how long those oscillations were allowed to proceed. So if you take me a photo, you show me a photo of this, and the photo looks like this, or if it looks like one bump or multiple bump, it tells me about the speed of sound times how long the system was allowed to evolve. Okay, so I think this is the Fourier space picture for those BA oscillations. And I think that's kind of the most rigorous one. That's the one where I think that's what actually is happening, and that highlights the importance of those phase coherence. But there's another picture in real space which maybe is more straightforward to think about at first. And it's the idea that, so you have a certain L value characteristic for those bumps and wiggles, and you can convert that L value to a certain angular scale. And that angular scale, it turns out, is a key angular size or a key size. And the idea is that if you start with sound waves and you allow them to travel after they enter the Hubble scale, you allow them to travel between that time and when the CMB is emitted, they will travel for a certain distance. And that distance is what we call the sound horizon. So that number is about 150 co-moving megaparsec. It's how far can sound waves propagate between basically the Big Bang and the CMB. There's a nice visualization of this where you can imagine in real space an initial condition that would just have a bump at some position. You have the same or a related bump in dark matter, baryons, photons, et cetera, because these are adiabatic initial conditions. And if once you unfreeze the initial condition, you allow it to evolve, what happens is the following. You send outwards a sound wave. I wish I could pause this. So maybe, let's see if I can play it again. So redshift is here, and the wave propagates, and at some point redshift will hit 1,000. And when that does, blue and red here, which are photon and baryons, start to decouple. So let me do this again. If you focus on blue and red, baryons and photons, they are tightly coupled, the wave propagates, and then after redshift of about 1,000, they decouple. And this bump here sort of gets stuck for the baryons. And it gets stuck at a distance of about 150 megaparsec, which is how far could that sound wave propagate before decoupling. And so it helps to think about this scale here as the angular scale corresponding to this sound horizon at the distance of the CMB. And the sound horizon is speed of sound times how much time could the sound propagate. Any question on this? Okay, if not, so this discussion explains why you have those bumps and wiggles in the CMB. But it doesn't sort of explain the envelope of why does it go up and then go back down. And so this is the next thing that I would like to explain to you all. And so one effect is called radiation driving or gravitational forcing. And I think a good way to think about it is this animation from the Wenhu tutorials. So what happens is that the gravitational potentials do evolve in time as a function of the expansion, but they do so differently in the matter and radiation era. And so the universe was first in a radiation-dominated era. And so, okay, you have a wave, so the gravitational potential oscillates just like the density oscillates. But in the radiation era, the potentials actually also die away. Whereas in the matter era, they actually stay constant. And I think that was your question. And so for the Fourier modes that started oscillating early, the modes that were unfrozen early during the radiation era, their potential as it oscillates actually decays. Whereas for the modes that started oscillating late in the matter era, their potentials oscillate but don't decay. And the decay of the potential actually enhances the oscillation. So this is what this animation is trying to show you. You can imagine you have this potential well, and you have a compression, a standing wave in that gravitational potential. But if the gravitational potential dies away when you're at first compression, then the next bounce will be just much higher. So this is sort of like the intuitive explanation. You have this oscillation within a potential well, but if the potential well dies at the right time, then when you bounce back, the oscillation will be enhanced. And so this produces an envelope that looks like this as a function of L. And so at low L on large scales, it's 1, so no effect, because again, these are the large scale modes that do not feel this decay of the gravitational potential. Whereas for the modes on small scales that oscillated during the radiation era, the potential died away. And so here you have a plateau. This amplification you can show is a factor of 5 in temperature or 25 in power spectrum. So yeah, the units are a bit strange, but that's the factor of the amplification. And so what it means is that instead of having a power spectrum like this with bumps and wiggles to the same amplitude, the power spectrum has an extra envelope on it that amplifies the bumps. So this is called radiation driving. And it's important because by looking at where you have this transition between no amplification and amplification, it tells you about when matter radiation equality occurred. So this is a key scale in the CMB power spectrum, is where does this amplification start, and where it starts tells you about how much matter versus radiation is in the universe. Okay, another thing you may have noticed is that, okay, there's this broad envelope that goes up and goes down, and we'll talk about why it goes down in a moment. Another feature is that the bumps are not sort of monotonic. You have a high bump, another higher bump, and then they're all lower than each other. So why are some bumps higher than the other? This is an effect called baryon loading. So baryons do a number of things to those sound waves. Okay, so the first one that's called baryon drag, really in this case is extra inertia from the baryons. And it just says that in the sound wave, the pressure, the restoring force is from the photons. But some of the inertia is from the baryons. So the baryons are kind of just a dead weight in there that add a weight but no pressure support. And so if you started with a normal oscillation in time, but you added some baryons, if you think about this picture of oscillations with spring, if you increase the mass, basically you shift the 0 point of that spring lower. And so your oscillation now is a bit asymmetric. So the compression might be deeper than the rarefactions. And so when you take the power spectrum, which is, it's kind of the absolute value or the modulus squared of this quantity, you see that some bumps will now look higher than the other. So you get an odd-even bump asymmetry. And so that animation here shows you how much the odd-even bump height changes when you change the amount of baryons. There's other effects in there, but please only look at the effect of the odd-even bumps. And so by measuring the odd-even bump amplitude asymmetry, you learn about how much baryon density is in the universe. So that's interesting, right? From from this effect, you learn about when matter radiation equality occurs. But since you know how much radiation is in the universe from the CMB temperature, this tells you about how much matter density is in the universe. So you measure the scale of this, you learn about how much matter is in the universe. Then you measure the odd-even bump asymmetry. It tells you how many baryons are in the universe. Okay. Other baryons effects, maybe I'll skip this and first start talking about diffusion damping. So we discussed this envelope of amplification. So why doesn't the CMB power spectrum go up all the way here? And the effect causing here is diffusion damping. And diffusion damping is what happens when the tight coupling between the photons and the baryons start to give away at recombination, and the photons and baryons start to be able to diffuse from each other. They're no longer tightly coupled. So this animation here, for example, shows you a certain Fourier mode with fluctuation in density of baryons and photons, and it shows you how individual photons might be diffusing away. And so if you allow your photons to diffuse away by a length equal to the wavelength of the perturbation, then that erases the wavelength of that perturbation. And so the photons are able to diffuse by a certain amount, and the fluctuations will be dampened if they're smaller scales than that amount. And that's why you go from this envelope to that envelope with a damping that's actually exponential or Gaussian, whose scale is determined by the diffusion scale of these photons. Okay. I think that's all I wanted to say about the Sachs-Wolf term. So again, this potential that we see at the surface of last scattering. We've talked about the baryonic acoustic oscillations, which typical scale tell you about the speed of sound and how much time between basically Big Bang and the CMB. We've talked about the amplification, which tells you about how much matter there is in the universe. We've talked about the odd-even peak heights, which tells you about how much baryons are in the universe. And so you can already see that by looking at the features of the power spectrum, you can learn a lot about the composition of the universe. My next steps will be to tell you about the other term, so the Doppler term, this Doppler boost due to velocity, as well as the integrated Sachs-Wolf effect. But I think given the time, maybe now is a good place to pause and maybe ask for questions. So thanks for your attention.
Why the modes evolve independently? The Fourier modes.
The Fourier modes. Oh, yes.
Yeah.
That's a really good question. So why can I say that this Fourier mode just oscillates on its own and then that Fourier mode oscillates on its own? I think that's, again, the same features that's the same reason why Fourier transform is such a good Fourier transform. When you have a linear system of partial differential equations and there's no explicit space dependence or time dependence in those equations, when you Fourier transform it, you get, instead of partial differential equations, you get algebraic equations for the Fourier modes, or sorry, ordinary differential equations for the Fourier modes that are independent. So whenever you have a system of PDEs that has no space or time explicit dependence, you Fourier transform and you get ODEs that are independent for each Fourier modes. And so, right, so the key factor here is, again, the translational invariance. And the other one is linear theory. So the PDEs have to be linear. And so when you go beyond a linear theory, the different Fourier modes actually get coupled. And that's what you learned about last week in the perturbation theory for the large-scale structure. So at linear order, all the modes evolve independently. At next order, they get coupled.
Hello. So can you explain again what does the adiabatic perturbation implies?
Right. Yes, and so maybe I should have put a summary of this. But basically, in single field inflation, my sort of naive way of thinking about the generation of the initial conditions is that during inflation, you have this a constant Hubble scale, and you have this accelerated expansion, just like if you had a universe with just dark energy. And you know how in dark energy, the physical energy density is constant. So if I take a box of the universe and I expand it, I have now two boxes, but each box had the same energy as before. So basically, during inflation, the same thing happens where the physical energy density is not changed during the expansion. But what happens is inflation will end at slightly different times at slightly different places. And when it ends, that same fixed amount of sort of energy is converted into standard model fluctuations. And so when I have this single field fluctuations in the inflaton, different patches of the universe stop inflating at different times. And they all get the same kind of energy per unit volume, but at a different time. And so if I now look at the same time everywhere, some patches will have had a bit more dilution post-inflation than others. And so the patches that stopped inflating earlier will then be underdense. And so really, the way I naively think about these initial conditions from single field inflation is it's the same universe everywhere. It's just some places are a bit ahead of time, and some places are a bit behind. And if you ask for a certain homogeneous universe, what happens when you look at it ahead of time or a bit late? If you take that same universe a bit later, the density in everything has gone down, but by slightly different amounts because radiation and matter redshift away differently. So those adiabatic initial conditions respect this. The ratio of density in matter fluctuates, so delta matter over delta photon is the same one you would get if you just take a uniform universe and just expand it a bit longer. So you have this one-to-one relationship between delta photon, delta matter, etc. I hope that helps.
Hi, thanks for the lecture. Could you go back to the animation of the BAO,
Yes.
please?
The real space one,
Sorry?
the one in configure
Yeah,
space, yes.
the left one. So could you explain how each of these different components evolve in this
Yes.
animation, please?
Yeah, I'm sorry. There's really a lot going on in this animation, and I should really have split it up in a bunch of times. But OK, so first, you start with a peak in all of these quantities, and that's what's meant by those adiabatic initial conditions. I think the y-axis might not be correct and might get rescaled over time. So don't look so much at the amplitude, but look at the shape for each of the components. So again, if you look at baryons and photons, as you allow that sound wave to propagate outwards, you can see that blue and red are on top of each other. And that's what tight coupling means. When you send that sound wave away, it's a wave in both photons and baryons. So I'll do it again. But that stops to be the case at redshift of about 1,000, where I wish I could freeze it, but you see the photons start traveling out, whereas the baryons stall. And that's just saying what was driving this sound wave was the pressure from the photons. So the photons were traveling outwards, carrying the baryons with them. Once they decouple, the photons continue their lives, but the baryons are just left stranded. And if you keep going in this animation further, so again, a tight coupling, the wave travel outwards at redshift of 1,000, the photons start traveling and leave the baryons stranded. What happens then is the dark matter, maybe we should look at what the dark matter did this whole time. While the photon baryons were sending their waves, the dark matter, so the amplitude here that's rescaled, but really the dark matter potential wells were actually getting deeper and deeper. So if you start with an overdensity in matter, it's going to collapse under gravity and get deeper and deeper. So don't trust the amplitudes on this plot. But right, so you see the dark matter was just collapsing and getting deeper and deeper. And then once the baryons are no longer feeling the photons, they start to feel the gravity of the dark matter. And now black and blue start to move towards each other. And so mostly the baryons move towards the photons, towards the dark matter. And so the baryons start to collapse in the same potential wells that the dark matter had formed. But the baryons remember a bit their initial bump, and that bump gets transferred to the dark matter. And this is why you have baryonic acoustic oscillations in the dark matter, which is not baryons. And then later on, as the galaxies form tracing the dark matter, they will trace this curve, which looks very much like the BAO correlation function. Thanks.
Yeah, hi. So in the high L regime, you were saying that, for instance, the photomean path gets, is it smaller or bigger? I forgot now.
Right, so you have a certain photon mean free path.
Yeah.
You have a photon diffusion length,
Yeah.
which is the mean free path times kind of square root of how many bounces you did.
Yes.
And that is roughly fixed. But what that does, what that does is it does more damping for smaller scale fluctuations than for larger scales. Really, you're just comparing the scale of your fluctuation to the scale of the damping. Okay. And I should have written it, but basically in power spectrum, it's e to the minus L squared over LD squared.
Mm-hmm.
So it's really just a Gaussian smoothing. If you take an initial fluctuation, but you wiggle the particles by this amount, you will completely erase fluctuations on scales smaller than the damping scale, and you will basically do nothing to the scales much larger.
And the potential wells generated by by the dark matter there, do they have any effect on this, like in the sense of nonlinearities being more important there?
Right. So I guess the silk damping is only a damping of the fluctuations in the baryon photon fluid. The only effect I think of dark matter there is that it changes when this radiation driving occurred. So. Okay. I guess in that sense, the main effect of dark matter, I think, is a background one.
Tá,
Because if
okay.
you're in the matter era, you don't get this dying potentials, but if you're in the radiation area, you do. Yeah, I probably shouldn't call it a background one, but yeah.
Okay, thanks.
Thank you.
Okay, if there are no more questions, let's thank Emmanuel
Thank you.
again.